So we've made it to our final section, which is all going to be about Stokes' theorem. You might also hear this called the Kelvin-Stokes theorem, or it's also called curl theorem. And so what this does is it's going to give another way to evaluate a line integral over a closed curve, kind of like Green's theorem does, but it's something else on the inside here. It's actually going to kind of relate to a surface integral, so we'll see a connection between these two. So I'm going to start by stating it again, and then I'll try to give you the physical interpretation, or at least the meaning behind it. But Stokes' theorem says, let S be an oriented piecewise smooth surface that is bounded by a simple closed piecewise curve. Which we'll call C, with orientation consistent with the surface. Then we're going to let F be the vector field, which has components P, Q, and R, where these have continuous partial derivatives on an open region in R3 containing S. Then what we can say is the following. So I'm going to draw just a little picture to kind of give an idea as what all of these things are before I give you the actual statement of the theorem. So what happens is we have some surface here. Let's say it looks like this, S. And it's got a border that can be piecewise. Maybe it looks something like this. Okay. This has an orientation that is consistent with the surface. So if this has outward orientation, it's going to have that counterclockwise around that edge there. So this is our normal vector N, and this is that closed curve C. Okay. What I can do is I can relate the surface integral to the line integral. And I accidentally wrote a y, that is the z-axis. So if I want to find the line integral around this closed curve, so the line integral of a closed curve C of f dot dr, what I can do is I can relate it to this surface integral here. So it's a double integral over the surface S. And what's going to go inside is going to be the curl of the vector field, dot product with that normal vector, and then integrated with respect to the surface. Okay. So what you can think of, the curl, remember, is the gradient cross product with the vector field. And then we're going to dot product that with that parameterization of the surface that matches the orientation. And then you integrate with respect to u and v. Okay? So this is given that this vector is consistent with the orientation of S. So if it has upward orientation, then this vector should have a positive z component. If it's downward orientation, this should have a negative z component. So essentially what this theorem does is it kind of gives us insight into what this curl actually is. I told you it's kind of the tendency of it to curl in place, but really what this theorem is stating is that this line integral is basically seeing what is the tendency of the fluid to evaluate along the boundary of the curve. Well, by relating it to a double integral, what's happening is this is really relating the collective measure of the tendency for this to rotate over the surface. So it's taking the collective measure, the rotational tendency over the entire surface, and that's equal to the tendency of that fluid to rotate along the boundary of that curve. Okay. So again, you can look up more stuff on this, but that's the best explanation I can give you in a short time frame. What I'm going to do is I'm going to show you that yes, this does indeed give us exactly what we want. And I'm just going to do a single example on this. This one's a lot more difficult than divergence theorem, and it doesn't always give you the nicest integral, but at least I can show you that yes, you'll get the same thing evaluating a line integral as you will with Stokes theorem. So let's look at this example. We're going to let F be the vector field y minus z, z minus x, x minus y. And we're going to let S be the top of the sphere x squared plus y squared plus z squared equals 36. That's above the plane which is z equals 3 root 3. We're going to let C be the boundary of S with counterclockwise orientation. So that means that the sphere also has upward or outward orientation. Okay. So the first thing we're going to do is we're going to evaluate this line integral without using Stokes theorem. But I want to go ahead and I want to draw this surface and this curve that we're working with. So we've got the sphere, the top half of the sphere, which is z equals the square root of 36 minus x squared minus y squared. And that's basically been sliced by this plane z equals 3 root 3. So I'm going to draw that intersection, but S is this surface. And to find this curve, which is where we sliced the sphere at with counterclockwise orientation, our z is specifically equal to 3 root 3. So if I plug that into my formula for the sphere, that gives me x squared plus y squared plus 3 root 3 squared is equal to 36. And if you think about 3 root 3, distributing that square would give you 9 times 3. So this is plus 27 equals 36. And so subtracting that over gives us a nice circle of radius 3. So this curve C is when z is 3 root 3, and x squared plus y squared is equal to 9. Okay? So we're going to go ahead and we're going to evaluate the line integral over this closed curve of f dot dr without using Stokes theorem. So that's exactly just calculating a line integral. What I need to do is I need to parameterize this curve. And since it's a circle, I'm going to use my trig formulas to do that. So looking at the parameterization of z, we can use the vector function r of t. It is a circle of radius 3 with counterclockwise orientation, so that's exactly what our normal circle is when you have cosine and sine. So the x component is 3 cosine of t, the y component is 3 sine of t, and then the z is fixed. It is 3 root 3. And the value of t to go fully around the circle will be 0 to 2 pi. Okay. And then also just to refresh, because it's been a while since we've done a line integral over any curve, we have the line integral of f dot dr. What we do is we find the values that t varies between. You take f and evaluate it along the curve, and then you dot product it with r prime of t and integrate with respect to t. So I definitely need to find the derivative of this. That will give me negative 3 sine of t, 3 cosine of t, 0. And then looking at my vector field, that's y minus z, z minus x, x minus y. So evaluating this along the curve, my y is 3 sine of t, my z is 3 root 3, then we've got 3 root 3 minus x, and then we've got x minus y. So I need to dot product this with r prime of t, and that's going to be what we integrate over. So I'm taking this piece and dot producting it with this piece. So going through the multiplication of those components, multiplying the first one will give us negative 9 sine squared of t, and then we'll get positive 9 root 3 sine of t. Second piece is 3 cosine of t times all of these. So that gives us 9 root 3 cosine of t minus 9 cosine squared of t. And then luckily at least the last one, because that piece is 0, this adds nothing to it. And now we hope that things simplify, and thankfully they do. So you've got negative 9 sine squared minus 9 cosine squared. That condenses to negative 9. And then we've got 9 root 3 sine of t and 9 root 3 cosine of t. So we've got everything we need now to actually evaluate this line integral. So this becomes the integral from 0 to 2 pi of negative 9 plus 9 root 3 sine of t plus 9 root 3 cosine of t, integrated with respect to t. So the antiderivative of negative 9 is negative 9t. Antiderivative of positive sine is negative cosine. And the antiderivative of cosine is positive sine. And then this gets evaluated from 0 to 2 pi. So plugging in 2 pi gives us negative 18 pi. Cosine of 2 pi is 1, so this is negative 9 root 3. And sine of 2 pi is 0. Plugging in 0 gives us 0. Cosine of 0 is 1. So that gives us minus 9 root 3, and sine of 0 is 0. So this gives us negative 18 pi. Then you have minus, and this turns into a plus. So those cancel each other out, and this ends up equaling negative 18 pi. Okay. So not too bad of a line integral, and really, the line integral is actually going to be a lot easier than using Stokes theorem. This isn't like the divergence theorem or Green's theorem where things turn nicely. This definitely is a little bit more complicated because it's a single integral turned into a double integral. And it's turning into a surface integral, so I've got to do more work than just parametrizing the boundary. But it is a connection that is important to relate these two things together. So again, I'm only going to do one example of this. Now we're going to evaluate this line integral using Stokes theorem. So that means I'm going to turn this into a double integral over the surface of the curl of the vector field dot product with RU cross RV, and then integrated with respect to U and V. So I'm going to start just by bringing this surface down because we're going to need it to be able to parameterize the surface and figure out all of the components. So looking at our parameterization of S, you can indeed use spherical coordinates, but it's definitely harder because figuring out what phi has to be to just go down to here would be a little bit complicated. So it's going to make a lot more sense to just go ahead and use that format. The x and y are whatever they want, and then the z component is the square root of 36 minus x squared minus y squared, since it's the top of the sphere. And then what's going on is these x and y are in this region R, and that region R is exactly this circle of radius 3. Okay. All right, so now we need to figure out these partial derivatives. And again, you've done this a bunch. That's 1, 0. This will end up being negative x over the square root of 36 minus x squared minus y squared. The partial with respect to y is analogous, but 0, 1, and then negative y over that same square root. Okay. And now I want to take the cross product and I want to make sure it's consistent with the orientation. And because it had clockwise or counterclockwise orientation, that tells me these normal vectors are going to be upwards. So if I take the cross product of these two, it'll end up being kind of what we did with the divergence theorem. This will be x over the square root of 36 minus x squared minus y squared, y over that same square root, and then the z component is 1, which is indeed consistent with the orientation. Okay. So what I need to do now is I need to find the curl of my vector field because it's going to be dot product with this very soon. Okay. So looking at the curl of F, I got to put my ijk, and then I got to put my partials, and then I put my vector field in the bottom, which just as a refresher is y minus z, z minus x, and then x minus y. So if you go through and do this, it's going to actually be really nice. So again, we strike and strike for the first component. Partial with respect to y is -1. Partial with respect to z is 1. So it's -1 minus -1. Moving on to the second component, we have to overall negate it. And then if I go through, the partial with respect to x is 1, partial with respect to z is -1. So that gives me 1 minus -1. So we get 1 plus 1 in that piece. Next up, we go ahead and strike this. Partial with respect to x is -1. Partial with respect to y is +1. So the curl of this vector ends up being a nice constant vector, -2, -2, -2. Okay. Now, if this had a variable, you'd have to again evaluate it on that particular parameterization, but thankfully it is just constants. So I'm going to go ahead and I'm going to take the curl of this vector field, and I need to dot product it with that normal vector, which is Rx cross Ry. And this is going to be what goes inside my integral. So this is -2, -2, -2, dot product with x over the square root, y over the square root, and then 1. So that dot product will end up being -2x over square root of 36 minus x squared minus y squared. Then -2y over the same thing. And then at least this last one is just -2. Okay. So you can go ahead and you can condense these two here and make it at least one single fraction. And then they both have a -2 in common, so I'll go ahead and factor that out. And then we have a -2 down here. Okay. So I want to go ahead and I now want to set up my integral. So to find the line integral over this curve C, instead we turn it into a double integral over that surface, but in this case it's found by using that region R, and then on the inside we put exactly what we just found. And then our region R is that circle of radius 3 in the xy plane. So if I want to evaluate this integral, instead it's going to make a lot more sense to use cylindrical, or, well, in this case double, it's polar coordinates. So here we're going to go ahead and immediately switch this over. This becomes the square root of 36 minus r squared. X gets replaced by r cosine of theta. Y gets replaced by r sine theta. And then we have to add the r dr d theta. Our r is changing from 0 to 3, and theta is changing from 0 to 2 pi. Okay. So distributing that r, this ends up becoming the integral from 0 to 2 pi, the integral from 0 to 3 of -2 r squared times cosine of theta plus sine of theta over the square root of 36 minus r squared. And then we get a minus 2r. So looking at this integral, it's kind of complicated. If I were to try to integrate this with respect to r right now, the second one I could do, but this first one is a little complicated. Okay. I also cannot separate these because I have r and I have theta intertwined here. However, because I do have constant bounds, I can switch that order of integration without having to worry. So hopefully, if I switch this order, it will make life a little bit easier, and we'll see. So I'm going to integrate from 0 to 2 pi first for theta. So we're just changing that order. So integrating with respect to theta is great because this piece just stays attached. It's a constant. And then if I find the antiderivative of cosine of theta plus sine of theta, that would be sine of theta minus cosine of theta. And then the antiderivative of negative 2r is negative 2r theta. And this gets evaluated from 0 to 2 pi. And then we go ahead and integrate this with respect to r. So this gives us the integral from 0 to 3. This negative 2r squared stays attached. Square root of 36 minus r squared. And then if I go ahead and do this, sine of 2 pi is 0. Cosine of 2 pi is 1. And then we go ahead and we plug in 0 as well. Sine of 0 is 0. And then cosine of 0 is 1. And then we do the same thing here. We get negative 2r. Plugging in 2 pi gives us 2 pi. Plugging in 0 gives us 0. And then this whole thing is integrated with respect to theta. And the beauty of doing this is negative 1 plus 1. This piece ends up completely disappearing. This just becomes 0. So we end up getting the integral from 0 to 3 of negative 4 pi r integrated with respect to r. Made a mistake back here. We just plugged in theta. Okay. So finding the antiderivative of that gives us pi r squared over 2. So the number out front becomes negative 2. Evaluated from 0 to 3. Plugging in 0 does nothing. So that just gives us 9. And it gives us the same exact value, negative 18 pi. But you can see this way is definitely more complicated. But there is that connection between surface integrals and line integrals because there's a lot of physical applications that's going on here. The other thing what this tells us is if I had the same boundary curve when I'm dealing with different surfaces, it's not going to matter because the line integral, think of in this case, has a fixed output. So as long as the surface has the same boundary curve, you'd end up getting that the line integrals or those surface integrals would all be the same. Okay? So do your best on these. This is definitely the hardest of all of our named theorems that we have, but it does tie everything we've done in together this semester and closes that chapter on vector calculus.